And it is now my great delight to introduce Dr. Dario Gil, who is Vice President for AI and for Quantum Computing for IBM. And his presentation is on information theory and the future of computation. Dr. Gil.
Thank you so much.
Applause, guys. I got the team.
Well, thank you. And first, let me thank Mira for the wonderful invitation to come here today and be able to spend time with all of you. It's a real pleasure to be with you. This is where I work. This is the T.J. Watson Research Center, which is the research headquarters of IBM, although we have 13 different laboratories all over the world, including one here in Haifa in Israel. And one of the great privileges that we have in the laboratory is the wonderful set of speakers and collaborations and scientists that come to visit us all the time. And a couple years ago, we had actually a filmmaker come and give a presentation on a wonderful documentary called Particle Fever. I don't know if you've gotten a chance to watch it, but if not, I highly, highly recommend it. It's one of the best documentaries I've seen in popularizing science. And this traces the discovery of the Higgs boson, one of the grandest physics experiments ever conducted. And the filmmaker is actually a particle physicist by training as well, in addition to being creating films. And one of the major characters in the film is another particle physicist from Stanford, Professor Dimopoulos. And in the film, he said something that really captivated me about, what differentiates the best scientists. And he said this. He says, the thing that differentiates scientists is purely an artistic ability to discern what is a good idea, what is a beautiful idea, what is worth spending time on, and most importantly, what is a problem that is sufficiently interesting, yet sufficiently difficult that it hasn't yet been solved. But the time for solving it has come now. This ability to discern when is the right time to solve a problem is a unique ability, right, that indeed distinguishes some of the very best scientists, but also the ability to generate and formulate beautiful ideas. And today I want to share with you a couple of beautiful ideas in the realm of computation and information theory. And one of them dates back to sort of like the foundation of information theory in itself. And we've learned from looking, say, at pictures like this to appreciate the fact that something as different as a punch card or DNA do have indeed something fundamentally in common. And what it is that they're both carriers of information. And we learn from giants in the field like Claude Shannon and Alan Turing to be able to think about information abstractly. And that this world of information can be separated in the original formulation neatly from its physical implementation. So the fact that we have been able to build computing systems that were electromechanical and vacuum tubes, or semiconductor devices, that we could maintain that theory and that separation from the world of physics and this abstract world of bits. What is interesting is that that idea was so powerful and in many ways fueled the information revolution that we have witnessed. And yet, in some fundamental ways, it went too far. And there were other physicists in this case who started looking at this question and started probing and asking whether this separation between information and physics was really that drastic. And, two of the early pioneers in asking these questions were, IBM fellows Rolf Landauer and Charlie Bennett, and I'll talk a little bit more about Charlie in a second, who's one of the fathers of quantum information theory. And what they basically ask, coming from this world of physics, is to say, well, is there a fundamental limit to how energy efficient computation can be? And surprisingly, right, they found the answer to be no. And they started exploring even things like the thermodynamical reversibility of computation and things of the sort. And they did many seminal foundation and work on this space, but that led Charlie and some of his collaborators to start asking what were the other intersections between the world of physics and information. And it led them to exploring the intersection between quantum physics and information. You see, I mean, for people like Claude Shannon and Turing, it's not that they did not know, of course, the nature of quantum physics, but from the perspective of information, historically it had been treated as a source of noise, as a nuisance to be dealt with, these quantum mechanical phenomena, and not necessarily as a feature that could be exploited to perform computation itself. This intersection between these different disciplines of information and physics, there was now a very famous conference that was organized jointly between MIT and IBM Research called the Physics of Computation Conference, and it was held at Endicott House in Massachusetts in 1981. And there were many wonderful attendees, just like in this conference, but the plenary speaker of the conference was Richard Feynman. And when Feynman was invited to reflect on this nature of the intersection of physics and information, he famously proposed the idea that it was time to really push forward in the idea of building a quantum computer, to bring this field of quantum information science and the nature of computation itself. And he said this wonderful quote in his classic, iconoclast style. He said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy." What he was referring to is that actually our ability to understand and simulate and model nature, it is inherently limited in classical approaches to computation, because fundamentally what we end up doing is doing an approximation from a quantum mechanical process to this classical binary process in computation. And that if we could create a machine that inherently operated according to the laws of quantum mechanics, we could simulate nature in a much more efficient manner. So I want to tell you about that journey and the fact that finally, after many decades, we can actually realize and build quantum computers. But first, let me give you a little bit of the background of how they work so you can develop an intuition for the physical mechanisms that I will describe right after. There are two things to understand on how a quantum computer works and the theory behind it. One is the principle of superposition, and the second one is the principle of entanglement. So we have learned with a conventional machine, what I would call a classical machine, is that we have classical states, meaning we have, in the case of computation, the famous bits, 0 and 1, and that these classical states are in these binary states, and that the entire definition of the state of a computer can be described by the description of each one of these individual bits in sequence, and that describes the entire state. Now, in the case of a quantum computer, we exploit quantum states. And what it allows us to do is to put the machine in a superposition of states. So in this case, we don't just have a 0 and a 1. In fact, we can have a 0, a 1, and both states at the same time. How many states? Exactly. That's a little bit of the entanglement. It's even more troubling in a second. How many states can we represent? We can represent 2 to the n, where n is the number of qubits, which is short for quantum bits, that exist in a computer. Now, there is analogies for superposition of states, with classical systems, but this type of superposition that you can create in a quantum computer is really very different, because you exploit a second principle, which is entanglement. And basically what entanglement says is that the states of these shared states, shared entangled states in a quantum computer cannot be described independently of each other. That you can have a perfectly orderly whole that is made of disorderly parts. And this is a famous principle that, a genius like Albert Einstein also struggled thinking about, which is, some of the famous examples that he made about the fact that, he called it spooky action at a distance as a criticism, but he wasn't correct about that. But basically, his idea, you could have two particles that share this entanglement, have these shared properties with one another. And you could send these two particles to two extremes of the universe. And that they act, if they share these properties, let's say when the polarization of one of the photons is up, the other one is down, as an example, they have this shared property, the fact that when you actually measure the property of one, they measure the state of one of the particles, you instantaneously alter the state of the other. And to first order, you would say, well, that seems impossible because you would violate the relativity principle and nothing can travel faster than the speed of light. It turns out you cannot use it to communicate information, but it is a true physical manifestation of how our world works. So superposition and entanglement are two principles of quantum mechanics that we're going to exploit to actually build a quantum computer. So now, why is it exciting? Why is it capable and powerful? The thing to remember of what is possible to do with a quantum computer is that the number of states that we're going to be able to have access to creating this superposition and entangled state goes as 2 to the power n. So the input to a quantum computer is always a classical string of bits. So you always need a classical machine working with a quantum computer to both send the information and then interpret the results at the end. So you have a classical string of bits. You get to represent the problem in these 2 to the n states. You perform your measurement, and then in the end, you're going to get a classical string of bits coming out. And I need not tell this audience, this exponential, but I always like to tell this apocryphal story that I'm sure many of you have heard about the inventor of chess that went to the emperor and said, here's this wonderful game I have invented. And the emperor said, well, would you like in return? And he says, well, something very simple. I would like just, 1 grain of rice for, the first square, and, I have 64 squares. And you just double the amount of rice that you give me every day. Right? And the emperor said, well, that doesn't sound like a whole lot. And, after a week of after a week, he had 127 grains of rice. After a month, there's more rice that he could consume in his lifetime. And it turns out that after 64 days, you need the equivalent of Mount Everest of rice. So 2 to the n is a very powerful number because remember, my qubits, if I can create a machine, and I'll tell you that we have actually built a machine that has 50 qubits, and that we're working on building larger and larger machines, 2 to the power of 50 or 2 to the 100 are very, very large numbers. In fact, by the time you have 200, say between 2 and 300 qubits, that's more states than there are particles in the entire universe. So if you devoted every particle of the universe to perform computation classically, you couldn't represent what a 2 to the 200 or 2 to the 300 states in a quantum machine. So it's a unique new form of computation that exploits a very different set of principles. So let me give you a bit of intuition about how an algorithm works in a quantum computer and why it could have some power. The first thing that you do in a quantum computer is that you put the computer itself in this superposition of states. So let's say if you have a 2-qubit quantum computer, you have 2 to the power of 2, you have 4 states, 0, 0, 0, 1, 1, 0, 1, 1 state. The second step is you have to inject the problem into the quantum computer. So now the states are represented in this block sphere by an amplitude and a phase that you're seeing there represented. And what it basically means is that the injection of the problem, you're changing the phase of the states that are being here represented. So you're making a modification to the states, to the superposition that you had created in the quantum computer. And the special property, the magic so to speak, is that now that you have all these highly entangled states, you get to interfere them with one another, and an algorithm is a sequence of operations that takes these states and interferes them like waves in the ocean in such a way that if you do this properly, the right answer gets accentuated. And the act of measurement tells you something about the problem and the answer to the problem. It's a very sort of abstract thing, but it's this sort of to have a feeling for, is this principle of interference of very highly entangled states that get you to answer to some questions. So why does this matter? Well, it turns out that with all the power that we have with classical computers, all the advances that we have made in computation, information theory has told us that we have actually a relatively small number of problems that we can actually solve. It seems like a lot, but there are many, many problems that have the characteristic that they grow up exponentially in terms of the number of variables we have that are simply intractable with a classical computer. And famously, one of these examples we'll talk about is chemistry, right? And which has very profound implications for, obviously for, the life sciences and development of new materials, etc. But there's other hard problems. So there are easy problems, things that we can solve in polynomial time. There are very hard problems, the famous problems like NP hard problems that you can solve in, they are basically non-polynomial in nature. And classical machines will never be able to tackle those problems. It's not a question of Moore's law or advancing the amount of computing. They blow up exponentially. Now, there's some famous examples of this, like factoring, right? And there was some interference. So here's an example of a mathematical problem that you cannot solve classically efficiently. And that is that if you take two prime numbers, P and Q, and you multiply them together, and I give you the product, and I ask you to factor that product, and you don't know what P and Q were, it takes you exponential time to be able to find them if those numbers are large enough. Now that problem, you say, well, who cares about that? It turns out that we've treated, because that problem is difficult to do, that's the basis of all encryption in the world. The fact that that problem is hard is the basis by which we encrypt all information. It turns out that if you had a large enough quantum computer, you can solve that problem in linear time. And that was a discovery that Peter Short, who was then at Bell Labs and now is a professor at MIT, did in the early 1990s. And he proved, right, theoretically, that that was the case. To give you an example. To give you a different example, it turns out our ability to simulate chemical processes with a classical computer is surprisingly poor. And the fact is we have to make all sorts of approximations that are inherent limiters to what we can do. So take as an example, and we could pick many, many examples of why this matters a great deal, but nitrogenase is an enzyme that is involved in the conversion of nitrogen to ammonia, and ammonia is a fundamental chemical element to the creation of fertilizers and food production and so on, and is a major energy consumption in the world. And if you actually look at the regions, right, 3 areas of this protein involved in the different reaction stages of this conversion, today, state-of-the-art, using some of the most advanced supercomputers in the world, even this sort of iron cluster that you see here on the left, which is just an element of this larger molecule, is very, very hard. It's at the limit of what can be simulated very, very accurately classically. Now, there's entire disciplines that have been created over many decades to perform these approximations in computation. But in the end, we're performing an approximation. The opportunity that you have with a quantum computer is that it turns out that, roughly speaking, you can map 1 electron orbital to 1 qubit. So now, if you're, the way, a stable reaction will form is as you bring these electron orbitals together, right, you have to solve Schrodinger's equations, and you have to be able to explore this interaction between the electron orbitals from one element to the other. If you can map in a one-to-one basis each electron orbital to a qubit, that's very powerful, because if I have 50 electrons, now I only need 50 qubits, order of. Whereas before, I was dealing with an exponential, 2 to the power of that number. So it fundamentally, over time, is going to alter our ability to simulate and understand chemical processes and nature itself, in addition to fundamental implications to optimization, machine learning, etc. So now, is it possible to build these things? I mean, this was a dream for many, many decades. Is it like I touched it? Still, okay, let's see this. It was a dream for many, many decades where this was going to be possible to be built. And what it finally has occurred is that we have achieved enough mastery of physical sciences and processes to actually be able to build some small quantum computers. And this is, let me show you a little bit of pictures. And actually, you can actually perform calculations in these computers for the first time in history. We couldn't do this before. Recently, in September, our team published, it was on the cover of Nature, to continue on the nature theme today. The largest simulations ever performed with a quantum computer, in this case, are very simple systems like hydrogen molecule and lithium hydride and beryllium hydride. But it still is a testament that the fundamental tenets and the principle, both the theory and the practical applications of this, are sound and are possible. And as we build more and more capable quantum machines, we will be able to simulate larger and larger molecules, and it will have very, very profound implications for how chemistry gets understood. So how does it work? What is the physical mechanism, and what do these computers look like? You're all used to the semiconductor chips, the famous chips that we all utilize in our phones and our computation. There is something analogous. There's different forms of quantum computing. In the case what I'm going to show you in the area we work, they're called superconducting quantum computers. And this is what a quantum processor looks like. What you're seeing here is an aerial view. The squares that you see, in this case, there's 16 qubits. Each one of those squares represents one of those quantum bits. And the little wiggly lines are resonators that allow us to couple one qubit to another. And that is the principle by which we can put these qubits in a superposition and in an entangled state. Now, the way we send the signals to the quantum processor is through these coaxial cables, and the information into a quantum computer gets sent as a sequence of microwave pulses, is the way they come in. And basically, you can establish a resonance with some of those qubits and resonators to be able to trigger the right state and either put it on a ground state or an excited state. You have to have a two-state system to create this qubit. And then those microwave pulses are the basis by which we can perform the operations, which is an algorithm in a quantum computer. Inside one of these qubits, that's an example of what one looks like. It kind of behaves like an artificial atom. So you have, like I said, this ground state, this zero state, and an excited state. And they operate, the whole quantum computer in this case, operates at 15 millikelvin, which is near absolute zero. It's 100 times colder than outer space, is how the quantum processor is operating. And the reason is because you have this tension. The reason creating superposition and entangled states is a very fragile and delicate system. And anything from the outside world, any kind of field, can alter and destroy it and get them to decohere, right? And you get back to a classical state. So how do you prevent that from happening? Well, one way is to isolate the system. And a way to isolate the system is to make it very, very cold. Now, if I make it perfectly cold, right, it's completely isolated, but then I cannot send my signals in and out. So it's this balance between isolation and being able to send my microwave pulses in and be able to extract the information out. That is the intersection of science and engineer to be able to build these quantum systems. So one very exciting thing that has happened is that not only were we able to start building some small quantum machines, so we built, I'll show you in a second, a 5-qubit system, a 16, a 20, and a 50-qubit system, all in the period of a year and a half. We have been working on this for many, many decades, as an organization. But one of the things we did is that when we built the first 5-qubit system, we put it on the cloud and we made it available to anywhere in the world to use it for free. In fact, we've done that for a 5 and a 16-qubit system. And we created a very simple interface, which is a drag and drop interface to perform. And what you're seeing here are some of these gate operations that you can do. It's the equivalent of the Boolean logic that we all learn, right? That is the bases, the ands and the ors and the nots. This is an equivalent set of logical operations that you create with quantum systems to be able to perform calculation. And this was made available for free for anybody. And it's been a really exciting endeavor because now what we've seen is like there's over 68,000 users in over 140 countries that have run 2 million experiments on the quantum systems. And there's been over 50 external publications that have been generated as a result of it. And it's being used now as a basis to teach, both in computer science and people studying physics, what is quantum computation? Because as I said before, not even the bit was sacred, right? The entire foundation of information theory, the entire foundation of computer science is being reformulated to be able to exploit this fundamentally new approach to computing that will have very profound implications. And as I said before, this is what, the inside of one of those quantum systems. They're very beautiful. That's what a quantum computer looks like in the inside of those dilution refrigerators. And we've shown also this progress of increasingly capable machines. This was something that was the realm of science fiction not so long ago, the fact that this was even possible to be built. So where we find ourselves is kind of the equivalent of the 1940s and the 1950s in computing. If you look at, this is the famous Colossus machine in the 1940s that was, used to be able to, break encryption during Second World War. And you're seeing like the large scale operation of it and, and the sort of, the complexity of it. And we've seen this evolution of what has happened until we can carry computers today. This is what a quantum computer looks like today. And in some ways, we're in that early stages. This is in terms of quantum computing. This is like the 1940s and the 1950s. But we're also going to see the benefit of all the history and all the lessons and all the capability that we have learned with classical computation applied to this. So this is going to greatly accelerate. It's not going to take us 50 years to realize all the benefits of what happened with classical computers today. But it's going to fundamentally alter the landscape of what computing looks like. And I'd like to, to finish with, in a second with a reflection, but what I want to point out is that when quantum computers reach the same level of maturity as today's machines, they're going to significantly outperform them on many tasks. Not at all tasks. Classical computers are always going to be here with us. There are many problems that don't map well to a quantum computer, but it is going to be a permanent aspect of how we perform scientific endeavors. And the area that is most exciting is the intersection of computation with material science and chemistry, and understanding the physical reality and the physical manifestation of nature will likely have very important implications. So I'd like to close with sharing one experience, connecting it back to this idea of generating beautiful ideas. And it's linked to the discussion we had about like the types of investments that we make in R&D and in science. And it's also an experience I had about a year and a half ago. I was attending a summit of CTOs in Silicon Valley, and there's a professor from Stanford Business School. His name is Bill Burnett, and he's a very well-known professor who studies sort of investments in R&D and in innovation. And he started by asking us, in a forum like this question of, when you have an idea, a good idea, what do you do? He asked us, what do you do when you have a good idea? And we all kind of looked sheepishly and said, I don't know, we tell somebody else, a colleague, and we share it with them. And I said, yeah, exactly, you tell somebody else. He says, so what happens if you share your good idea, your brilliant idea to your colleague, and they don't like it, they think it's a bad idea? What do you do? And, one of us was joking and said, I don't know, we tell somebody else, because what do they know? It's like, exactly, you probably will tell somebody else, right? And see if, they validate your idea. And he says, what are you doing in this process of sharing these ideas around? And sometimes, people validate it, sometimes not, but what are you doing with this process? He says, maybe one of the things you're exploring is to see if your idea has some consensus between perhaps people you respect, or you're going to need institutional support or funding, right? You're trying to see if you have some consensus. And he says, great. He says, at the intersection of this idea of seeking to see if your idea has some consensus and value creation, he said, what's better from an economic point of view? To have an idea that happens to be true, that has consensus, or to have an idea that also happens to be true, that does not have consensus? And we say, well, we know the answer to that. A non-consensus good idea is better, right? Because, at the extreme, you're the only one who has it, right? And you're able to go out and create a wonderful innovation or product into the world. He says, okay, sounds great. He says, what happens in most institutions, however, if you have a non-consensus idea and you're wrong? He says, you're a fool, right? It's like, here comes Dario with his good idea, right? We told him he was wrong. And sure enough, he went ahead anyway, and look at him, he failed. It's a big problem. And he said something really interesting. He said, innovation is the management of variance. And he says the process inside organizations to eliminate non-consensus bad ideas, quote unquote, eliminate all possibility of non-consensus good ideas. And the inevitable conclusion is you revert back to the mean. And I thought that was really, really interesting. And he shared, some venture capitalists in California are exploring this principle. And he says, when the principals get together to decide on investment, if they all agree that they should invest in the venture, they don't do it. because in all likelihood, they're going to revert back to the mean, and their business is not to be in the mean, it's to be in the variance thing. Right? So with that, let me stop and take any questions you have. Thank you.
Fantastic, very provocative. Thank you so much. All right, good. Questions? Yes, ma'am.
Can you please talk to the
These quantum computers can be used almost as enigma machines, and therefore, if it might be easy for them to crack encryption algorithms, is there a need to develop further encryption algorithms, algorithms and start changing?
So the realm that we are right now in terms of quantum computer is what is referred to as approximate quantum computers. And one of the characteristics that they have is that these kind of computers, like all computers, have errors. And the reason, that's problematic in a quantum computer is, like, if you've heard about, the uncertainty principle, one of the difficulties of it is that the act of observation alters its state. So in a classical machine, if you have an error, right, you can copy whatever you're calculating into memory, and every once in a while you can check in memory and then, reflect that state on the computation. In a quantum computer, you cannot do that, because if you looked at what was happening, you're destroying the computation in itself. So there is, to really be able to do that problem of factoring, you need what is known as a fault-tolerant universal quantum computer, meaning a quantum computer that can tolerate errors and can compute for an arbitrary amount of time, one. And two, you'll likely require, as a result of that, a computer that has millions of qubits, because the way to implement error correction imposes a lot of overhead in the number of qubits that you have to put into the system to be able to do this. So the short answer to that question is, it's probably likely many decades away, right? However, we know that it will happen. And therefore, it's very important to replace existing encryption algorithms with new ones. And NIST and many other groups were working collaboratively to design quantum-safe algorithms, because, it is an example of something of enormous consequence. If you're able to, create a machine that breaks that, quite literally, you could steal all the money in the world, right? Or you could do anything you wanted. So it's very important that that gets done, and it has to be done in parallel, but we have time to do it.
I have an inevitable question for you.
Yes.
What is the relationship between the human brain and the quantum computer? Is there a relationship or an analogy or a metaphor? What do people think in your area about this?
There are some people, David Deutsch, as an example, have this sort of model of the brain based on quantum information and so on. I'm not supportive of that. I think it's very risky on quantum information to perform a lot of analogies, and that's when you end up in very loose footing. It's a realm because it looks so, quantum information looks so bizarre from our classical day-to-day life. A lot of people have proposed lots of metaphors and analogies to it, but inevitably when we do, we end up sort of missing the cue of what is the actual underlying physical mechanism that is happening, right? So this idea of entanglement, there is no classical analog, right, that would allow us to derive an understanding of what is happening. You just have to, follow the math and understand the physical process, and you have to develop a new intuition to think about it. So I would be afoot if I try to perform any kind of mapping, let alone in the brain.
So can I ask?
So if you look in 10 years from now and think of personal quantum computers, so how would you solve the cooling problem?
Through the cloud. So I don't think in 10 years we are going to have any kind of form of, carry quantum computer, but we're going to benefit from having quantum computers. So the model of computation is going to be on the cloud, and then you're just going to perform your calculation on the cloud and then benefit from it, but you will not carry it with you.
Would superconducting materials help?
Yeah, so there are proposals for ways to implement this, right, at room temperature and so on, but it requires, you know, major material science and device breakthroughs. So in a decade, I mean, maybe that's many, many decades away, but in a decade, I still think that the primary form of quantum computation will be these superconducting-based devices.
Okay, so I agree. No, don't go places. Okay, so I think we are agreed that we would be foolish to think of a quantum computer counterpart of the human brain, let alone his brain. It wouldn't be enough. You need too many qubits.
Too many.
But is there any other biological system you can think about that would be appropriate? Not necessarily the brain as the right counterpart, so to speak. Of course, when you've done those calculations on basic, simple molecules, you probably picked those because it was the simplest thing you could come up with. But presumably for the next, you know, there is the notion of overlapping one qubit and one orbital. So there are principles that I guess you can use to see what would be the chemical equivalence you want to go after. Can you think of anything like that for biology? So it's got to be entangled, it's got to be overlapping.
I think it will address it more at that fundamental. I mean, from the chemistry angle all the way up. I mean, as the systems become more and more capable, to the extent that some of those first principle calculations, but in terms of like a direct mapping to a more macro system, like a biological system, I'm not aware of like a theory that does an equivalent mapping to the electron orbital. I know what you're asking, like, but there's no.
I'm
we
just
haven't
asking for intuition, not for reality at this point. But I'm
well,
maybe,
it could.
maybe barking in the wrong
You know,
direction.
so, but I'll give you a different kind of answer. I think the answer is going to be less on sort of theoretically grounded and more empirical in nature. So take, for example, machine learning.
It's not bottom-up. It's a
Exactly.
top-down
So
approach.
take, for example, machine learning today, right? So what we've seen in the advances of machine learning is an area where, in some fundamental ways, we have abandoned causality, right? And we've done this mapping of a very, very large input space to an output classification space by mapping into these neural networks that have very, very high dimensions. There's a very active new field emerging at the intersection of that kind of representations and quantum computing, because now I can map into this, you know, Hilbert space, right? This, you know, tremendous 2 to the n state that I can have on a quantum computer. And to the extent that I can heuristically do this mapping, right, perhaps of a life sciences process or, you know, a biological process to this in some way that it allows me to do either classification or something, you know, that is a pure heuristic with no
fundamental
grounded
identification.
yeah.
Yes.
Then maybe there's something. So look at the, back to the analogy of the 1940s with classical machines. At the beginning, people really struggled to figure out what they could do with these computers, right? And people, we could do ballistic trajectories and things like that. And obviously, after many decades, we understand that we can apply it to all sorts of things, right? And most of those advances were people trying things out through heuristics because they had access to the machines. I think we're going to see that kind of renaissance in quantum computing because until very recently, it was all theory and proofs. But now you can try things out. And to the extent that clever people are able to map the problems to the representation of a quantum computer, I think there'll be significant breakthroughs. And that's probably the best direction I would give.
Fantastic. My suggestion is immune system, just for the record.
Okay.
All right, Mira, we said, okay. Well, great presentation. Thank you so much. Fascinating.